Okay, let's talk about the geometric mean. So the geometric mean, I think we'll work through a motivating example to kind of show you where it comes up, but it's important in a few different contexts, but probably the most commonly kind of applicable context is in finance. So let's say we have an investment, and at time zero, we have $100 in our investment account. Now let's say that year one is a good year. Year one, we have a rate of return for that year of 50%. So at time one, if we have a rate of return of 50%, we get to keep our original stake and we get 50% more. But year two was not so good. We get minus 50% in year two. Now, if I consider these percentages as data points like x1 and x2, I might be tempted to just average them together and say, okay, on average over these 2 years, I got plus 50%, minus 50%, average the two, they average to zero. I might be tempted to think that at time two, I just end up back at $100. I had net zero rate of return. But if I lost 50%, oh, this is a plus 50%. If I lost 50% in year two, that means I took what I started with at time one, and at time two, I only had half of that. So I started with 150. At time two, I have 75. So saying my average rate of return is zero, that probably doesn't correspond with the behavior that I would expect from a statement like that, right? In this case, I ended up losing $25 over the course of those 2 years, not breaking even over those 2 years. So what's really happening if I give this, say, the number a or the variable a of t looks like, and call it a naught, it looks like a bunch of 1 plus rates of return multiplied together. Or in this particular example, a of 2 is 100 times 1 plus 0.5 times 1 plus negative 0.5. So really what's happening here is these contributions are coming in multiplicatively. They're coming in as a geometric progression, it's called, instead of an arithmetic progression. So really what I would like to do, I would like to respect that geometric progression, that multiplicative idea that's kind of going on in the background here. So I would like to find a mean rate of return, let's just call it R, so that if I got that constant rate of return every year for these 2 years, that I would have the same amount at the end. That's what I would like to be true of a mean rate of return, right? That's kind of what was true of the average, is that if we replaced each of our data points that are kind of all over the map, if I replaced each of them with the average data, the average of the data, then the sum of the data would still be the same, whether I use everybody as the average or everybody scattered about. So same thing here. If I replace my variable rates of return with this quote mean rate of return, I would like to choose a mean rate of return that sets these two equal. So I see I have 1 plus R squared is 1 plus x1, 1 plus x2, or I have 1 plus r is the square root of 1.5 times 0.5. And if I calculate that on the calculator, I'll just keep my screen share the same, but you can do this on your calculator. So if I do square root, so that's second x squared of 1.5 times 0.5, that gives me about 0.866. And then I'd like to subtract 1 over, so my mean rate of return is 0.866 minus 1 is 0.134. Oh, with a minus. So had I lost 13.4% per year, what would my time to amount look like? So this is time 0, 1, 2 amount. We start with 100. The first year I lose 13.4%. So I'm down to what? 86.6. And then if I lose 13.4% again, I end up with 0.866 times, and then 1 minus 0.134. And that gives me 0.74995, or right on 75. So if I were to take these variable rates of return and kind of level them out, make them the same rate of return, I see that 13.4% loss, that would be the correct way to think of the average rate of return in this sense, where after 2 years, I would be at the same place, whether I use the variable rates or the constant rate, the mean rate. So this is what we call the geometric mean rate of return. And for a general data set, y1 through yn, that are all positive numbers, the geometric mean is the product of all of those data points to the 1 over n power, the nth root. Now, I am saying that this is a mean. We would kind of expect it to be related in some way to the arithmetic mean. And it does turn out that this is related to the arithmetic mean. So this is kind of an aside. If we log the geometric mean, we log the product of y1 through yn to the 1 over n power. As an aside, if you're not familiar with the log, not a big problem. This is just kind of this is just a little extra information to show you how the geometric mean relates to the arithmetic mean. One of the properties of the logarithm is that powers inside of the log become products outside. And another property of the log is that the log of the product of things is the sum of the logs of the things. So what I see is that the log of the geometric mean is the average of the logged data points. I can take the log of each data point or each data value, take the log of each of those, and then average that transformed data, and that will give me the log of the geometric mean. So the log of the geometric mean is the average, the arithmetic mean of the logged data. And last is the harmonic mean. So let's look at a motivating example here. Let's say that I go on a road trip and I travel at a speed of 60 miles per hour for 1 hour. Then I travel at 30 miles per hour for 1 hour. What is my average speed? Note that I traveled for equal time in this case. So equal time. Well, I could compute average speed in two different ways. Maybe I do, I'm not sure if this will work, but let's see if it does. Maybe I do 60 plus 30 over 2 is 45 miles per hour. Or I could just do this the long way, right? I know that how far did I travel this first hour? So this is 60 miles per hour, 30 miles per hour. How far did I travel the first hour? I traveled 60 miles. How far did I travel the second hour? I traveled 30 miles. What was the total amount of time that it took me to travel 90 miles? 2 hours. So this is 90 over 2 or 45, and my units are miles per hour. So I can compute the arithmetic mean of my two data points, 60 and 30, or I could do it the long way, and I actually do get the same answer. What if my data was reported slightly differently? What if I had traveled 60 miles per hour for, let's say, 60 miles, and I traveled 30 miles per hour for 60 miles? So here I've gone equal distance at each of these speeds. If I do the same thing, do I get the right answer? Well, my X bar is 60 plus 30 over 2 is 45 miles per hour, seemingly for my average speed. Is this consistent with what actually happened? Well, how far did I travel? I traveled 60 miles plus 60 miles. I traveled 120 miles. And how long did it actually take me? Going 60 miles an hour for 60 miles took me 1 hour. Going 30 miles an hour for 60 miles took me 2 hours. So it took me 3 hours to go 120 miles. Or this is 40 miles per hour. Note that these are not equal. So if I travel different speeds for equal distances, I can't just average the speeds together. If we thought of an extreme case, what if I had said 0 here, and if I had said 0 here? If I drove 60 miles an hour for 1 hour and then parked and ate lunch or something and drove 0 miles an hour for 1 hour, does that make sense? Sure. It would just have taken me 2 hours to go 60 miles. I'd have driven an average of 30 miles an hour, 60 plus 0 over 2, just fine. But what about this one? Can I go 0 miles per hour for 60 miles? If I'm not moving at all, how long will it take me to travel 60 miles? It'll like take forever, right? This seems like it should take like infinite time or something like that. So we clearly see that this is a different structure we're working with here. If we travel equal distances at certain speed versus equal times. Equal times, we can average things like normal. Equal distances, it turns out that the harmonic mean is the way to go. The harmonic mean is is n over 1 over x1 plus 1 over x2 out through plus 1 over xn. Or another way to look at it is that 1 over the harmonic mean is the average of the 1 over the data. So 1 over the harmonic mean is the average of the 1 over data points. Feels similar to the geometric mean, right? Where the log of the geometric mean is the average of the logged data. Here, 1 over the harmonic mean is the average of 1 over the data. So let's try this with this data up here, where we had 60 and 30. Well, I have 2 data points. And my data are 60 and 30, so I have 1/60th plus 1/30th. Well, I want to, in the denominator, I want a common denominator of 60, so that's 1/60th plus 2/60ths over 60. So that gives me 60 times 2 over 3 when I flip my fraction of the denominator. 120 over 3 is 40 miles per hour. And that does mesh with what I would expect. So that's the idea of the harmonic mean. When my data points are represented in such a way that, say, for speeds, they're representing equal distances traveled, I want to use the harmonic mean as a measure of center, because if I use the arithmetic mean, I still can compute it. I can add 60 plus 30 over 2, that, nothing blows up. But I get a number out that is not really that is not really helpful, right? The idea of what is the average speed that I traveled is, if one car was driving a variable speed and another was driving a constant speed, what speed would the constant speed car have to drive so that they both get to the destination at the same time?